All right, so it has even air, helium, they're all elastic. What does that mean? Well, if I have two molecules, right? If I have two molecules of air, is the air moving or is the energy moving through the air?
Energy.
The energy is moving. If I'm saying something to Soroya, the air is not moving, but the sound is moving. Clear? Yes? So elastic is simply when it goes like this. It goes like this. It comes back, right? So it goes. This one goes back, then this one goes to the next one, then the next one, they come back to where they were, basically. They're not moving. It's just the energy that's moving. So sound is energy traveling through a medium. It's not the medium that's traveling, it's the sound that's traveling. And the more elastic that medium is, the faster it's going to go. And iron, which is iron and carbon, there are other things that can make it. You can put in molybdenum, you can put in nickel, you can put in chromium, but the main two ingredients would be carbon and iron. Clear? Yes? Easy? Let's talk. I don't have it on the board, I forgot it for some reason, but resonance. We've talked a lot about resonance. So one thing I can do in life is I can resonate. Resonation, and I had a talk with Mael, I think, about it. See, look, if I excite something, my sinuses, right? And I excite them with an energy pulse, right? And they're going to make a sound. I'm going to make a sound. And that sound is going to be at its natural frequency. So my sinuses have a natural frequency, right? So this is what happens. I keep bombarding that sinus with energy. Because I know, you may not know, but I know. Weird, I know. But I know, and you don't know, and you may know, but you will know in a moment.
Too many no's.
Too many no's. I'll take no cheese on my pizza. Now, so if I excite that sinus, it's going to make a wave. Now, if I keep exciting it at that natural frequency, it's the same frequency, right? So you get this giant constructive interference because it's the same frequency wave, right? Same frequency, same wavelength, everything. So what happens naturally when I excite something at its natural frequency, I am going to construct the wave. And the construction of waves that have a frequency equal to the natural frequency of the object I'm exciting is called resonance. That's what resonance is. So I know what this frequency is. Put it all together. I know, terrible. I know, painful. Okay, but that's resonance. Okay, so be careful of the options they give you, and choose wisely. Okay, so you know what constructive interference is. Constructive interference is when you have two waves and they're the same. And you get when it will construct and it will go like this. So it'll be loud. Correct? Now, you guys have had, or maybe don't have, but wish you had, or may have had, headphones.
Yes.
That, they have a little speaker in to listen to extraneous noises that are coming from the outside. And what it does is it takes those noises and it generates waves that are the same, but shifted. okay, in such a way, so that's a noise. So what the earphones will do, it will make an opposite noise, right? And what you get is when this is destructive interference, you get this. Okay? Now, so that's it, right? Now, remember we did the Slinky demonstration, correct? Yes?
Yes.
Thank you. Nice resonating. Okay. So, if I send a pulse, when you have a fixed rope or fixed slinky, and I send a wave down it, right? What's that called? I just said the word. It's called a pulse. It's called a pulse. So I sent those pulses down the wave, right? They're waves, but they're called pulses, right? Yes? Like you can have them like this, right? These are two consecutive pulses that I sent down the slinky, right? Or when the pulse goes down and comes back, it looks like this, right? It goes down, the first one went down, and then when it comes back, it's underneath. It flips, right? Yes, yes, yes. Now. So they're pulses, correct? We know what a pulse is. Do you remember? What happens if these two pulses meet? What happens? No, these will construct and become a bigger pulse. Right? They're like this. Remember the first one where I had this?
Oh, you're saying you have two constructive pulses?
Well, yeah, these two pulses are both exactly the same wave.
I thought you were saying
If they meet.
Then it
No, I understand. This is going to construct. There's a picture on your test saying what's going to happen to these
I
two
was
waves.
doing the
I
constructive.
hope they couldn't have those that heard me because.
We have it on tape. We are going to revise it.
Right, so this is going to be.
I was referring to the constructive and destructive together. They cancel each other.
Now, this is two separate terms: constructive and destructive. Constructive is when they become larger, when they add. Destructive is when they subtract. Okay? So if the pulses are on opposite sides, they're going to destruct. They're going to cancel. Understood? Now, this pulse may continue past it, but at the point where they meet, it's going to be zero. Now, this pulse may continue on its way underneath, that's fine, but when those pulses meet, these pulses here, they will destruct. Absolutely destruct. Understood? These will absolutely construct. Clear? I think we're almost done, guys. We are almost done.
Now what?
Press, trough, pulse. Okay, now we just got a little bit more over here. Can you move that over here? Just so we're-
The iPhone.
Listen, I don't want to disturb. I'll put it a little bit of a slant. That's perfect. Okay, so one thing that I've got to remind you of, and that is that you've seen soccer. No, it's fine. It's perfect. You've seen soccer games or football games, etc., and sound will drop off very quickly. So this is how sound travels. Think of right here, no walls or in place. Right here, at the tip of my pencil, is a dot. Right? It's a little tiny ball, infinitesimally small. Okay? Right like that. Put a dot in the air. It's right there. No walls with you, right? Now, it's a little test dot, I'm going to call it. Okay? Now, from that test dot, it's going to make a very loud noise. And it's going to travel, as all sound travels, in a sphere. Right? All sound travels in a sphere. Sometimes those spheres are deformed because the sound's traveling here, my head's in the way, but the sound behind me, you can hear me, right? Can you hear what I'm saying?
Yes.
Yeah, of course you can. So it basically travels, though, if you put a test dot, it would travel in a perfect sphere out in an ever increasing diameter, ever increasing radius. It's a little bit clearer based on what I want to say. Now, the relationship between the intensity of the sound and the distance the sound has traveled is this. And it is that the intensity of the sound is inversely proportionate to the distance squared it traveled. Okay? Or you could say this. You could say, I purposely put that D there, of the radius of the sphere. Okay? You get that? So sound, the intensity of sound drops off very quickly. So, what's the problem? It's okay? Did it drop? It wasn't on?
It was on.
Why'd you touch the screen?
Battery low.
Say what?
Battery low battery.
Battery low? Okay. So we're okay for a few minutes?
Yes.
I'll be done in a few minutes. Okay, good. So, I don't know where I was. What was I saying? Was there anybody listening to me? Dangerous question to ask a class of physics students at 10:30 in the morning, near the end of the school year. I was talking about intensity dropping off. Okay. Yeah. So it's an inverse square relationship. Light is too. The light intensity. If I have a light beam, let's say I have a little bit of a source light right here, right? And it's very bright. As I go, I know what I was going to say. As I go away, it's going to drop off. So in other words, if I go 1 meter, the intensity will be 1. 1 over 1 squared is 1, right? If I go 2 meters, it's 1 over 4. Yes? If I go 3 meters, it's 1 over 9. If I go 5 meters, it's 1 over 25. If I go 10 meters, it's 1 over 100. If I go 100 meters, it's 1 over 10,000. So it drops off very, very quickly. Do you understand that? Okay, enough said. And then the rest of it is simply this. You have, oh, this is trough, this is peak. Oh, the Tacoma Narrows Bridge, I talked about that. That was a standing wave that was formed, and a combination of standing waves and resonance. So that was a pulse wave, I guess. Okay, Tacoma Narrows Bridge. You can look on the internet for that. The speed of light, don't forget this is also light and sound. So the speed of light is 3 times 10 to the 8th meters per second. I'll put some equations on the board because there's no notes tomorrow, so I'll leave some of this on the board, all right? And yeah, oh, beats. Like let's say, shall I give you a problem that's right on the test?
Sure.
All right, if I hear 5 beats, okay, I hear 5 beats, yes? I hear 5 beats, and I know one tuning fork is 350 hertz. What's the other one? There are 2 answers. It's either going to be what or what? Nobody? Yes. 355, right? Read 355 hertz or 345. Right? You get it? Yes? So it's just that yeah. If I have 2 frequencies and one is 353 and the other one is 358. How many beats am I gonna hear? 5 beats, right? You get it? Yes? Oh, and also, this is a tricky one. Don't forget to change this. Because you have to, the things have to be in hertz, meters, seconds. Right? Yes? So you have to change this. So this is 100.9 times 10 to the 6 hertz, right? Okay? You get it? You all right? We're done. Well, pretty good, huh?